All right, so the first thing that we have to know for organic chemistry is that it's not as bad as others say, or it's not as scary as others say. The reason is that we are all afraid of things we don't understand. So if you do get to understand organic chemistry, you will understand. I guarantee that you will appreciate the beauty of it, and you will appreciate how elegant it all is. Just like learning any new thing, you will need to learn a few new terms. Some of them you have already seen in O levels, but we will be using those as well as adding more to them. So today, the whole point of this lesson today is first to understand why we need organic chemistry. Thing is, life is complicated, right? And we need that complication, that variety in life to make it going. And just like that, we have organic compounds. They may seem complicated, but you can make sense of them, and that variety is important to keep things the way they are. Uh, there are two main characteristics of these compounds that we will rely on. One is that they form these long chains, and that is called catenation. And that is something that allows carbon to be such an important compound for life, carbon to be such an important element for life. Basically, what carbon does is that, let's suppose I have hydrogen and I want to join it with another hydrogen. And yeah, that's it. I can't make any longer chain here because both the hydrogens have shared one electron and they're good to go. That's it. That's all they could do. But I can do catenation with carbon, with nitrogen, with sulfur, with with oxygen. It doesn't go beyond O3 because then it has to join this. That's a very weird smile, but that's the structure of ozone, basically, this thing. So that's the limit because oxygen needs to share two with each other. So they don't really go on like that. But carbon allows us to make these long chains that may go up to even 50,000 atoms or even more in one long chain. Sure, that becomes a really, really insanely large molecule, but that is still possible. Catenation is that they're able to make these long chains. And not just those long chains, we can convert them. We can make rings out of it. For example, I could use four carbons, and instead of making a long chain, I could join them together. Of course, I'm adding hydrogen to make sure every carbon has four bonds, but this is a ring. This is a four-sided ring. I could make a hexagon like that. Basically, every corner is carbon. Okay. So I could just show this. And when I do that, that is implying that I have carbon with as many hydrogen required to make its four bonds. But that's what carbon is. And the catenation allows it to do that. And not just that, sometimes you can also make double bonds. And those double bonds can be shown within the ring itself like that. And then if you have multiple double bonds, it's also possible because of the properties of carbon. It is also possible to transfer those double bonds. For example, I can have them here, here, and here. And then the next instance, very next instance, the bond transfers over here and here and here. And that we show as a ring, that you're able to get these rings, you're able to get these transferable bonds because of carbon. So basically, you're able to form these long chains. If I had this chain, I could show it like this, like one carbon, join with another carbon, join with another carbon, join with another carbon, another carbon, another carbon. And that is one way we can show these chains. So catenation allows me to do that. Catenation is one carbon joining with another, that joining with another, that joining with another. Of course, if you get all of them as carbons, you're getting diamond, you're getting graphite. And but if you don't get all of them as carbon, you're getting different compounds. So three main categories of these organic compounds. Ones that are long chain, like these chains, every corner is a carbon, or you're getting these rings. A pentagon would mean that I have five carbon atoms on each side, all bonded with each other singly. Or I could have these rings, and these rings will have circle in them, and this circle shows that the bond is transferring from one atom to another, to another, to another. So these two, we call them aliphatic compounds. So if you have these long chains, those are aliphatic. And within the aliphatic, we have another group which is cyclic. So this one is cyclic. That is a cycle made from these carbon chains. And then we have another one which is aromatic. All right, and they get their name from aroma because these usually have very strong smell. It can be a really good smell as well, doesn't have to be a bad smell. So we have the ring ones are called aromatic because they have smell that is can be sweet, can be pungent, depends. And you have aliphatic in which you don't have these rings that I'm talking about. Transferable bonds don't exist. All right, so we have classified them as that. So that's the first thing. We have chains and we have rings, and within the rings, we have transferable bonds, which make it aromatic. In AS, we will be dealing with these. That is AS, aliphatic compounds. And this is A2, aromatic compounds. To understand aromatic compounds, we might need to rely on a few concepts from AS. So pay attention when you're studying that. That's one. Both of those things come together for biochemistry. Biochemistry is the chemistry that deals with life, right? So earlier on, people thought that organic chemistry is what the chemistry of life, but then they realized there was this guy, Friedrich Wöhler, and what he did was that he got salt, like it was cyanate, if I remember correctly. So he had some cyanate, ammonium cyanate, if I'm not wrong, and he converted it to urea with no other byproduct. And that was so amazing because people thought that ammonium cyanide is inorganic and urea is organic. People thought that urea could only come from biological processes, like it gets its name from urine. But ammonium cyanate was salt made from totally inorganic substances. And Wohler showed that actually they're not two, but they're one, and one can be converted to another, or the other can be converted back to the inorganic one. And that is how they said that, all right, now we have biochemistry. That's the chemistry of life. And then we do that. Okay. So that's one, how many categories of substances we have. Next is uh, how we show them. And there are multiple ways of showing the same compounds. Of course, you know all about, let's say, I say ethane, sorry. So this is ethane. Now, that is one way of showing what ethane is. But another way of showing what ethane is this one. This is also ethane, right? So you can see that there are two carbons in the middle. This one is ethene, by the way, not ethane. And not just that, you can also show them as CH3, CH3, or you could show it as C2H6. Or you could also show it like this, that there's a carbon in the middle and there's one hydrogen at the top, one hydrogen at the side, one hydrogen at the back. So the back is shown as a, what do you call? Let's show one hydrogen at the back. So the back is shown with a dotted line. One hydrogen at the forward. So this is shown with a wedge. All right. And then the next carbon. And that carbon also has one hydrogen at the top, one at the back, and one at the front. So, and one on the side, obviously. All right. These are the OEM ones. Yeah. So this is basically a three-dimensional structure. I will not show carbon here. Instead, what we'll do is that we will have just these wedges here. So the dotted line means it's behind, it's inside the uh, glass that you're looking at, the screen that you're looking at. And the wedge shows that it's outside, it's sticking out towards you, outwardly. And that is another way of looking at what this is. And there's another way of drawing the same thing. I have two carbons joined together. So one corner and the other corner. And there you go. Now, all of these are basically different ways of showing the same thing. This one is its molecular formula. This tells me what that thing is, how many carbons, how many hydrogens, how many elements it has, how many atoms of each element. Then this one is called structural formula. This tells me that starting from one side, how do the carbons join with each other and what is joined to every carbon. So here's how it goes. So starting from the left side, I see the first carbon. Okay, what is joined with that carbon? It has 3 hydrogen. All right, next carbon. What does that carbon have? 3 hydrogens. Okay, Next, no, nothing. All right, that's it. But if I want to see all of them expanded out, we get this formula, which we call displayed formula. And in this one, we show all of them, but in a two-dimensional structure. I'm not telling which one is behind, which one is in the front. I don't care. I just want to see all of them separated out. And this one is called a 3D formula because it is telling me what is behind it, what is in the front, what is on the side, all of that. And this one is called a skeletal formula because it does only tell me the skeleton. Now, skeletal formula will never include hydrogen. It will never include carbon. Like you will never write carbon, never write hydrogen. But everything else you will write. Every nitrogen, every oxygen, even OH sometimes we write all of that. Okay. So that's a skeletal formula. All right. So here's what I'm going to do. I'm going to do another example of this thing, and then I'm going to ask you to attempt that. So molecular formula of this thing is C2H6O. Okay, that tells me what the ratio of each element is, but it doesn't tell me how they're arranged. So if I want to know how they're arranged, I will need to look at the structural formula. All right, so my structural formula, instead of saying structural formula, I think everybody is more comfortable with displayed formula, so I'll start with that. This is ethanol. Okay, fair enough. I did not write hydrogen because remember, hydrogen is a filler atom. If a carbon needs to make 4 bonds and it doesn't have anything else, 4 hydrogens we give to it. If a carbon needs 2 more, we just give it 2. The other 2 will be bonded to something else. So wherever you don't see anything, that's hydrogen. So this is the ethanol. What is the structure? Let's start from the left side. Now I'm writing carbon first. So this carbon has 3 hydrogen attached to it. Okay, so CH3. And that's it. I talked about that carbon and whatever is attached to that carbon. Okay, then I have next carbon and I have 2 hydrogen attached to it. Okay, so CH2. I have O with H to it. That's my structural formula. It is telling me individual carbon wise that what are you seeing as you go from one side to another. Next, what is my skeletal formula? My skeletal formula is easy. I have first carbon joined with second carbon, and that is joined with OH. And that's my skeletal formula. I don't need to mention how many hydrogen it has. For example, this one has 1 bond, right? So I can automatically see that it has 3 other hydrogen. And this one already has 2 bonds. So I know that the other 2 are going to be 2 hydrogens. So it's, if I were to write it again, this is how we'll do that. It is this. That's ethanol. There you go. Pretty easy to write. And then I have 3D formula. 3D formula for a compound like ethanol might not be required from you in the exam, but we can easily draw it. So I have a carbon here, which is attached to 1 hydrogen at the back, 1 hydrogen in the front, and 1 carbon on the right. And that's also attached to 1 hydrogen at the top, 1 at the back, 1 in the front, and it might be joined with the oxygen, which is probably joined with hydrogen in the front. It doesn't have to be like that. It could be hydrogen at the back or something. But this is just one way of writing it. Okay, so that's how you do that. So these are my 5 different forms of these formulas. All right. Now, obviously, we don't use all of them for all the compounds. Depending on which atom is bigger or which molecule is bigger, we change the complexity. For example, if I had this compound, like, now look at it. It has so many carbons that if I try to make a displayed formula of it, or if I try to make other formula, any other, it will be a mess, really a mess. But this 3D formula really helps me out, tells me what is in the front, what is at the back, how it is joined, everything. So it's a pretty simple molecule, to be honest. It's really not that big of a molecule. But skeletal formula or 3D formula is the best way that we have of showing or conveying this information. But for a small molecule, like for example, propene, this one would do. So if I had propene, this one would be fine. I can show that, right? I can even use skeletal formula for this. In fact, skeletal for this would be an overkill. I don't really need skeletal for this. For example, I have 1 carbon joined with another, that is joined with another. And these 2 have a double bond. So I'll just show 2 lines here that they have double bond. You can also join the line here if you want. And that's propene. So skeletal formula sure, if you need it, if you really need it, but displayed is also fine. How would I convert it to a structural formula? Start from the left side. I see the first carbon, it has two hydrogen with it. Next carbon, one hydrogen with it. Next carbon, three hydrogen with it. And that's my uh, structure formula. Sometimes what the examiner does is that to show that you don't get confused, they might mention a double bond between these. And that is not strictly a structural formula, but they do that to make sure that you don't make any mistake. Okay, so here's what I'm going to do. I'm going to write a molecule here and I want you to convert it to its displayed formula, molecular formula, and maybe 3D formula if you can, but especially structural formula. So here's the thing. Okay, tell me, what formula is this?
Skeletal.
Skeletal. So try to convert it to its molecular, displayed, structural, and 3D if you can. I'll just explain this example and let's see if we can learn from it. So first of all, what's the main compound? This is an aldehyde because it has CHO there. And how many carbons? One, two, three. That's a branch. So I'll just start with that. So one carbon with three hydrogen, then next carbon with one hydrogen and one methyl. Okay. This parenthesis tells me it's a branch. Then the next is one carbon with two hydrogen. Notice that I hop from one to here, then straight here because this is a branch. And then obviously the next one, which is another carbon with a hydrogen, and that has a branch. The parenthesis tells me it's a branch. So CH3. And then on to the next one, which is CHO, which means it's attached to hydrogen and it's also attached to oxygen. So that's an aldehyde group. Now, how do I write its skeletal formula? No problem. How many carbons? I have 1, 2, 3, 4, 5 in the long chain. So 1, 2, 3, 4, 5. On the fifth one, I have CHO. So I'll just put this oxygen. I did not write hydrogen attached to carbon because I don't need to. It's assumed that carbon always has 4 bonds. On the second from the right, I have methyl. So that's just this. And on the fourth from the right, I also have a methyl. So that's just this. All right, so that's my compound. What's its structure formula? We already have that. Let's try to name this thing. It has 5 in the main chain. So that is pent, and it is also the aldehyde. So I'll call it pentanol. And then on the second carbon and the fourth carbon, I'm calling it a second because I'm starting from the right side where my main family thing is, the main functional group. So on the second and on the fourth, I have 2 methyl in total. So that's dimethyl. Again, how do you remember this? Locate, count, and then name. LCN. So how do you locate it? It's on the second and fourth carbon. Sure. Count them. There are 2 of them. Name it. Methyl. So 2,4-dimethyl pentanol. And based on that, I know exactly what compound I have right now. All right, now I'm going to give you another one and I would like you to draw that one. So I have 3,5-dimethyl hexanol. So here's how we should be able to do it. So I have the main chain is hexanol. So 1, 2, 3, 4, 5, 6. Last one has HO group, so H and double bond with oxygen. 3, 5. So 1, 2, 3. So this one has a methyl. 5, 4, 5. This one also has a methyl. And just fill the rest up with hydrogen. 1, 2, 3, 1, 1, 2, 3, 1, 2. And yep, that's it. How do I write its skeletal formula? I have 6. So 1, 2, 3, 4. Sorry. 1, 2, 3, 4, 5, 6. Last one has double bond. Third has a methyl. Fifth has a methyl. And there you go. That's the thing. What you should do before the next class. So first of all, reflect on your understanding of organics so far. Do you understand how to name them? How do you understand what empirical, molecular, structure, displayed, three-dimensional formulas are, skeletal formula? Are you able to convert all of them for all the compounds that you deal with? You should be able to draw it technically, But of course, I wouldn't ask you to draw it for larger molecules. Like, don't write displayed formula for a really big molecule or something. You should be able to identify the functional groups that we have seen, the homologous series that we have seen. You should be able to name them. Okay. So, and one thing that really helps in organic chemistry I've seen is maybe get a study partner, somebody you can revise with. So see if you can make a group amongst yourselves if you can. Otherwise, obviously, you can just note things down, things that you don't understand, or things that trouble you, and you can share with me. And inshallah, we will all master organic chemistry. All right.